start this thing. Okay, so what we're going to go over today is a very common problem in computer science, and we're going to go over specifically algorithms that are a different runtime. So today we're going to learn about log n algorithms. Okay, so you don't need to know log n for the first exam, right? Oh, and I suppose I should mention about your first exam, which I just finished writing last night. So, okay. So I gave you your practice exam, and I used that as a model. And I'm not sure if I made it too easy or too hard, right? Because I actually think the programming questions on there are actually fairly easy, because some of them have like 2-line solutions if you're clever about it. So I'm not sure, but you know that's my perspective because I can easily see the answer because I've been trained to see these answers. Practice on a lot of these things makes it so these things are really easy. So the exam, you may have noticed that like the practice exam score, it didn't add up to 100, right? It added up to slightly more than 100, right? Yeah. So that's because a lot of times on my exam I give a bit of a buffer, where basically the score is out of 100, but it's possible to get extra credit. Just because there's more than 100 points on the exam, and if you give me really good answers, then or make some very interesting points, you can also get points that way. So if you point out, hey, this big O time is this, but actually technically it's this because we briefly went over this in class, you know, that's one way to do it. But there's a lot of different ways you can. But there's opportunity for extra credit on the exam. You're allowed to bring in one sheet of paper, front and back. So that's what you'll bring into this exam. Okay, and that's also for the second exam, one sheet of paper, front and back. Your final exam, I believe, is completely open. But if you bring in everything here, it's not that the exam will be too easy, but you're going to spend most of your time looking up stuff when you should be writing. Okay, so there's that. The last question is actually survey. So, well, basic survey. Survey implies it's more organized than it is. But the idea is that basically tear it off, okay, and that's a way to pseudo-anonymously basically leave some feedback for me. I wouldn't say anonymously because, of course, your handwriting could be matched to your handwriting, but I'm not going to do that, right? Because I have a standing don't be a jerk policy. If you really want me to do that, I can make sure to hand it off to different professors, so I'll never see it, okay? But the idea here is that if there's suggestions you have to make the course better for the next, couple of weeks, rest of the semester, then please, by all means, give me the suggestions. And the reason it's there for you to tear off is so that you don't have to worry about like defending me, which I wouldn't be anyway, because if I'm doing something wrong, then I'm not going to fix it unless somebody tells me I'm doing something wrong. So, okay. And again, there is one question on stacks in there. So hopefully the practice exam has a bit of hard problems, but they shouldn't be like ridiculously hard. They should be solvable for you guys, right? Okay. So today we're going to go over how to search an array recursively. So searching an array can be accomplished by using recursion. So the easiest way, though, is that the way we've learned how to search arrays is to do a linear search, which I'm not going to use recursion to write that because that's silly. I'm just going to write it iteratively. So public static Boolean search, and I should probably make sure you understand what the search is. Search item, right? The idea here is that I'm searching some list. Right, so public static item. I'm going to call this linear search. Or I'm just going to search some list for an item, right? Now, of course, this could be accomplished with the .contains method, right? But I'm just going to write it out over here. Just to make sure we understand this. Actually, I'm going to write this as briefly as possible. For EE in list, so for each item E in the list of type E, if E dot, if E dot equals, actually I'm going to have to rewrite this, but this should give you the basic idea. E dot equals the item. So if the item in the list is what I'm looking for, return true because it's in the list. I found it. Otherwise, return false. Right? So that's pretty simple and straightforward, right? I'm just going to check every item in the list, right? One at a time. And once I find it, I'm going to return true. If I don't find it, though, I'm going to return false because it wasn't in the list. This isn't too useful information, though, because it's just the same stuff it contains. A better way of doing that is to use int, right? To tell me what index I found it on so I could get it if I needed to. So in that case, I'm going to do -1 for false. And then that means I can't use this for each loop. So that means, of course, I have to do it like this. Let me go ahead and rewrite this method. Sorry. So I'm going to look for a target. So now for int I is equal to 0, I is less than list dot size. I plus. You know, the delete key on my laptop and the power key are right next to each other, and they both feel exactly the same. And you'd think this would give me more trouble than it has. But surprisingly, no. Surprisingly, I've not actually hit the power key accidentally. So now, list.get the current I'm looking at. List. So e item, make sure that e item is equal to list.get I. If the item at that index is not equal to the target, return index I, because that's where I found it, right? And this will return the first instance that I find of that object. So it's the index of method I just wrote here, right? Now this runs in O of n time. It runs in linear time. Why? Because worst case scenario, it's at the end of the list. Average case scenario, it's in the middle. Best case scenario, it's in the first area of the list. Okay, so it's a linear relation, but we don't care about the best case scenario, so we care more about the average and the worst case scenario, and on average, it's somewhere in the middle, right? There's a linear relationship between the amount of time I have to take to search this and the amount of things in the list. But we could do better. We can actually do better if the array is sorted. That's the key. If the array is sorted, we could search it. So binary search can only be performed on an array that is sorted. So we're learning something now called the binary search, which is basically the gold standard for searching stuff. And the idea here is that we're going to figure out a recursive method. But the easiest way to demonstrate binary search is to play a game, to be honest. So let's play that game. And it's a game we've all played before, and I'm going to play right now. I am thinking of a number between 1 and 100. Tell me what number. Make a guess of what number it is, and I'll tell you whether your number is whether my number is higher or lower. Okay? 50. So my number is higher. Higher than 75.
88.
It's lower than 88.
80.
Okay. 80. Right? It's lower than 80. 77 is my number. Okay. So what happened there? Why did you guys start at 50, by the way? It was half the list, right? By starting at 50, what were you able to do? If I said it was lower, what do you know? If I said my number was lower, what do you know about my number? It's got to be lower than 50, which means that it's not 51, it's not 52, it's not 53. It's not all the way that up to 100, right? And it's also not 50, right? So essentially, you were able to split my list into 2 piles, right? 2 piles, okay? You split my list into, so right, I have my array here, or my list, and I have a pile, and by asking that question, you could split, and getting an answer, you could split my my list into 2 roughly equal-sized piles, okay? We'll consider them equal for the purpose of doing a big O analysis. So, which is not here and here, right? Okay, so my answer was that it was higher than 50. So that meant it was in the range 51 to 100, right? So what was the next question somebody asked? Somebody asked 75. Why did you ask 75? Because that's in the middle of that. And by doing that, you were able to split that space up into, and getting your answer, you were able to get the answer not here and here. So by asking two questions, you reduce the search space to what proportion of the original size? 1/4, a quarter of the original size. Your first question reduced the space by half. Your second question further reduced it by 1/2. Your third question will reduce the original search space to what size? 1/8. So by asking those questions, you're continuously reducing the search space by 1/2. And this is what O of log n means. Every single time, basically it means that the problem can be continuously split in half. Okay? Or specifically log base 2 of n, right? Okay? Log base 2. So let's actually ask, so without actually getting into algorithms, let me go ahead and give you a really easy to understand definition of what a logarithm tells you. Log of n, so log base 2 of n tells me how many times I can split n into evenly sized in half, essentially. How many times can I split n in half, right? So if I've got, so let's look at log of, let's say 16, right? So log base 2, so what is 16, by the way? 16 is, and just to make sure you know the answer before we go in, so it doesn't surprise you, right? 2 to the 4th is equal to 16. So 2 times 2, 4, 8, 16. So now if I were to ask what log base 2 of 16 is, right? The answer is that, right, we do that logarithmic equation and say that's 4, right? But another way to think of it is, well, I can split 16 in half once, and then I can split the resulting thing into half again, and then I can split that result into half again, and then I can split that result into half again, and I can't split these things into half anymore, right? So did 1 split, 2 split, 3 split, 4 splits. So it's log 2 base 4. That's a much easier definition, right? So log base 3 would be what in that case? So if a log base 3 of n would mean I could split it into what? Three evenly sized piles, right? This is why, if you think about it, log base, so now let's do log base 10 of 100, because that's a bit easier to see for everybody, right? I can split it into 10 evenly spaced piles once, and then I can split each of those piles into 10 evenly spaced piles one more time before I stop, right? So that's my very easy definition of logarithms right there. Of course, it doesn't get into like well, what if it's 101, ha 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 ha, right? Right. Well, we don't care about that right now. We're caring about like splitting stuff in evenly because that helps us understand the big O notation, right? So log base. So again, we're dealing with so actually it makes log base 2, even though you thought log base 10 is pretty easy to deal with, log base 2 is even easier to deal with because, you know, it's very natural for us to say, okay, let's just split these into evenly sized piles, right? Okay, so the idea here is now if we're searching for something and that thing is sorted, we can use this same number guessing game idea to create a log n algorithm for searching the space using the same algorithm actually. What we're going to do is that we're going to look in the middle and see if that's bigger or smaller than our target, right? So let's go ahead and demonstrate on the board. Okay, the idea here is say I'm searching this this sorted list for the number 12. Okay, so 1, 2, 5, 12, 13, 72, 109. Let's see, 1. So how many do I have? 1, 2, 3, 4, 5, 6, 7. Yeah, let's go ahead and make sure that. Go ahead and 1, 2, 5, 12, 13, 14, 100, 101, 102, 103, 104, right? So here, right, it's not evenly spaced like give me a number 1 through 100, right? It's not evenly spaced, but it is sorted. Okay, so let's go ahead and give these indices, by the way. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 11 items in here. Let's see. Yeah, let's go ahead and say, I'm going to go ahead and make it a bit easier and go ... and say 200 over here at index 15, okay? Does everybody see that from your perspective? Okay, so that way there's 16 items in here, okay? I just wanted to make it base 2 just to make it easy for analysis. That make sense? Okay, so because since we're searching for 12, we don't really care about this other stuff over here, okay? So what we're going to do is that we could find this by searching sequentially, right? I could search 0, 1, 2, right? So I could search the first item, second item, third item, fourth item, find it in 4, right? We're going to see that that this is going to find it in the same amount of time here, which is actually the worst case scenario for this, okay? So the first thing we need to do is that we need to search this, since this is sorted, we can just kind of look in the middle, right? And we know that basically if the item in the middle is bigger than our item, then our item has to be to the left. And if it's smaller than our item, then our item has to be to the right, because our item is bigger. So let's see, where's the middle of this array? So it's 0 through 15. So it should be like 7 or something, right? The idea here is that what we're going to do is that we need to calculate that. What we're going to do is that we're going to take the start of where we're looking, start plus end, the start index plus the end index, and divide it by 2, right? And we're going to use integer division over here. So 0 plus 15 divided by 2, right? That gives me 15 divided by 2, which is 7, right? Using 7.5, which is round down to 7, right? Because we're using integer arithmetic here. Right? Good old integer arithmetic, where basically nothing really, where it's, easy. It's back to the 4th grade kind of stuff. So let's look at index 7. So how does 101 compare to 12, the item we're looking for? It's larger. So that means that basically, since we know this is sorted, we know that it can't be to the right of this, right? 12 cannot be in indices 8, 9, 10, 11, 12, 13, 14, or 15 because those are all going to be larger than the item at index 7, right? Right? So we can already rule out half the items in the list that we're looking for. Okay? So now, and we can rule out looking at this indice as well because, we just directly compared it and found it was not it. So that means the range that we're looking for now is in this. So that we are doing recursion here. Basically, we're asking the same problem just on a smaller subsample. So now we do binary search on this portion of the array, which is 0 through 6. So we need to find the middle of this. So 0 through 6, well, there's an odd number of items in there. So the one in the middle, which is 12. Ooh, I lied. We found it pretty quickly, didn't we? We search in the middle. Hey, 12 is 12. Awesome, we found it. Okay, so what if, though, it was instead like this? So, really, 12 and 7 over here. Okay, so now we look in the middle. How does 7 compare to 12? Sorry, it's smaller. So we know that it can't be indices 1, 2, 5, or 7, right? So we know now that if 12 is in this array, it has to be between 4, 5, and 6, right? So we now search this range over here. Okay, so how do we find the middle of this, right? It's easiest for us to see that the middle of this is indice 5. So how do we figure that out? Well, with the equation I gave you, start plus end divided by 2, right? 4 plus 6 divided by 2, so 10 divided by 2 gives us indice 5, so that's the middle of that range. That's how you find the middle of some of that range. So we check 14, it's smaller, then we just search this single number over there, right? So so this one is a bit different because here we have multiple base cases but also multiple ways that the recursion can go, because the recursion can go left or right. But it doesn't make that too much harder to write. So our base cases are the array is empty, which simply means that basically we couldn't find anything in there, right? Or that we found the item. That's another base case. We found the item, right? So our base case is basically if we're solving this problem recursively, remember the base case is something that's so simple that we can just say that's right. So the array being empty, we can say, ha, didn't find it, return -1. The array being examined matches the target. In other words, we found it. Return the indice that I found it at. Okay, those are easy comparisons. So the other results, so basically if the array is empty, return -1. If it matches, return the subscript. Otherwise, if it's less, go to the left. Otherwise, if it's if it's bigger, search the right half. So they have so here's their own where they're searching for Dustin. So they rule out that it can't be that half, then it has to be over here, right? It finds it very, very quickly. What's amazing is that basically, right, this is a small array, so it's hard to see the advantage here. But when we get much quicker, when we get much larger arrays, like one of this size, it would require only 16 probes to find it. Find it in 16 steps, something in the thousands. So log-based algorithms are almost like constant time good. They're not quite constant time, but honestly, no, everybody's gonna. If you find a log algorithm for anything, people get extremely excited. So the only problem is that of course this won't work on every list. This will only work on lists that can be sorted, right? So it only works basically if things are comparable. So public static. So remember that terms comparable. So public E, so here's where we have to use it basically for the first time. Comparable. So public E extends comparable E. This means that all the generics in here are going to be comparables. So they all can use the compare to interface, right? That's what this bit means over here. That we can, that when I say, that when I finish writing this out, int linear search, sorry, not, or let's call this binary search. Binary search. This means I can assume that basically that the list, the list of stuff that I'm looking for, that's a list of the E's in there are comparable, and that the E target over here is also comparable. So that means I don't have to like make my line super long by writing comparable stuff. All right. So let's go ahead and write this. So base cases first. Oh, well, actually, we do need a bit more information over here, unfortunately, right? We need the int start, the range that I'm starting my search at, right? And I need the int end, the range where I'm ending my search at. Okay, makes sense? Got to know where I'm searching between because it could be a big array. I don't want to, or a big list. I don't want to split this list up, right, into smaller lists because then I'd have waste memory, right? It's easier if I just search the indices. Okay. So let's go ahead and try this. Okay, so so let's go ahead and check this. So so how do I check if this range is empty? Well, if end is greater than or equal to, if the end is greater than the start, that's my condition for seeing if they're empty, right? Basically, if start is going to be on the left, end is going to be on the right. If they crisscross, like end is less than start, right? If they crisscross, then basically that means that the range doesn't exist anymore. Okay. If they so that means that basically if the range I'm looking for is a non-existent range, then I couldn't find it. So return -1. Okay. Else if actually I'll put this in an else. Else I got to look at the middle of the array, right? So I got to look at the index. So let's go ahead and just do some calculations. So int middle index Yeah, so actually I'll just call it middle. Start, middle, end. So int middle is equal to start plus end divided by 2. So common mistake here is just to leave it like this, right? But you got to remember your PEMDAS, right? Please excuse my dear Aunt Sally, right? So this would be start plus n divided by 2. Just n divided by 2, right? So this would work for your first call, but it wouldn't divide. So instead what you need is, it wouldn't divide to start by 2. So you need parentheses over here. Okay. So now, e item is equal to list.get middle, right? The item in the middle of that range. Whoops. So now, we've got the item in that middle, and now we can do our comparison right over here. Just we'll do it once and we'll save that comparison. So int comparison is equal to, let's compare middle. So let's compare target. So how you interpret the answer depends on what's comparing to what. So here I'm checking is our target, the item we're looking for, smaller, equal to, or bigger than the item I'm currently looking at. Okay. So first off, if comparison is equal 0. Remember, this will return 0 if they are equal in value. It will return something negative if target is less than the item that I just found in the middle. And it will return something positive if what I just found is greater. So if it's equal to 0, that's my other base case, right? I found it. Return middle, because I found it in the middle. Okay? Else, well, here's my recursive cases. So it's a bit weird because they're the middle, because it's the other base case is kind of tucked away right next to the recursive cases, right? But here we were essentially doing a null check first, right? In fact, we don't even need a else here because it'll just stop otherwise. So we can actually make it a bit easier to read that way. So if our comparison is equal to 0, else if, what if comparison is less than 0? That means our item we're looking for is smaller than the item in the middle. That means we need to search left, right? If it's less than the item I just found, I need to look all the way to the left. Otherwise, it might be greater than all the items I just found. And here I don't have to check. I could do this. Comparison greater than 0, but honestly, it's going to be equal to, or less than, or greater than. It's got to be one of the three choices. So if it's not one of the first two, I'll just write else. That makes sense to everybody? So if it's less than, what's the range I need to search? So I need to return the result of calling binary search, right? So now I need to basically make the problem smaller. Okay? So let's figure out these 4 arguments one at a time. First, I want to search the same list for the same target. So that's easy enough, right? That's easy enough to do, right? The next thing I want to do is that I need to figure out what's the start of the range I'm searching for. Okay, where am I beginning? Well, if I'm searching for the left, right? If I'm searching to the left, so if I'm searching the whole thing and I want to search the left half, the start is still 0. And if I'm searching this range for an item, this small range 4, 5, 6, well, if I search to the left, the beginning of the range I'm searching doesn't change at all, right? So it's just so if I'm searching to the left, the start doesn't change at all either. So all that's actually going to change is the end, right? So let's go back to looking at the whole range, right, where I started at 101. So what's the range I'm going up to? Well, I already searched the middle, so middle minus 1. That makes sense to everybody? I'm just going to search one left of middle, right? When we're talking about indices, subtracting brings us to the left. Middle minus 1. Okay, and so notice how it makes the range smaller, by the way, right? By now instead of the range being from start to end, it's from the middle item and actually a bit over, So we split it in half, the path in half. Sorry, the search space in half, and a little bit more than that, but it's a negligible amount. Okay, and then otherwise return binary search. Again, we're going to search to the right. So we're going to search the target, the list for the target. But searching to the right, we keep the same end, right? We're going to be searching to the other end. It's the start that's going to change, right? So we're going to go from the middle. We're going to search from starting from one right of the middle, right? That makes sense to everybody? Okay. Middle plus 1. So now we can search the entire array. And this is it. That's all I need to do to create a log n method. So let's go ahead and make a list. List of integer. L is equal to new array list. Not linked list here, because actually if it was a linked list, right, the get method would take O of n time. So right here I'm just going to do with the, so dealing with linked list would be a bit tricky. But let's just go ahead and work with array list and just keep it here. So new array list of integers. Java.util star. Now we've imported everything. Okay, array list for int I is equal to 0. Let's go ahead and create a random number generator so we can create, random rand is equal to new random, right? And actually I'm going to give it a seed so it runs exactly the same each time. So I is equal to 1, I is less than, let's go with 10, 20, bunch of items, I plus plus, L dot add I. And of course, all I'm going to do here is just collections dot sort. I'm going to just sort this list. So that's sorted now. Okay? Because remember, searching for this only works searching for a random list. Okay? And let's go ahead and binary. Oh, and one last thing. Let's go ahead and L dot add 13 so that we're going to search for the number 13. That way we can always find it this way. Okay? So system.out.println binary search. So now we call this binary search method, and we start from, we want to search L for 13. We want to start at index 0 and go, and our starting index is list dot is L dot size. Nice one. Actually, that makes it kind of. So let's just go ahead and run it, see that works. And it found 13 at index 14. Okay, in this list of a bunch of random stuff. I did. Oh, no, I didn't. So, sorry. List.add random, sorry, rand dot next int. There we go. And because I'm using it a seed, it will create the same random numbers each time. So it found it at that location. So it's always going to find it at that location, right? So let's go ahead and, but mind you, this looks a bit unwieldy, right? I have to provide, if I'm the user or the programmer, I have to provide my start index and the end index, and I could mess that up, right? And honestly, the method call should look like this. So a lot of times for recursive methods, what we do is that we make this private, okay? And what we do is we use something called a wrapper method to call this, which will look like this. It's going to just copy paste this over here, right? So it's going to be now public static so same calls over here, binary. So I'm going to overload this method, right? And it only looks for this list in the target. And now what I do is I just have one line here, just like the add method. So just like having the second add method. So return binary search list target 0 list.size -1. And this way allows us to basically, and what this allows us to do is that it allows the user to use this method easier. It allows us to, if we need a pass, like if we're doing tail recursion or something, we can now pass that without the threat of the user messing up or something. So that takes a lot of onus off the user for how this works. So this was at index 49974. So what I'm going to do is that let's go ahead and make it a bit easier to find for us. So what I'm going to do instead, just to make sure so that we can see that this works, just to prove that it's generating random numbers, I'm going to say so int next is equal to a random integer. Okay, if next less than 0, so if next is less than 0, next is equal to next times -1. Make it positive. Okay, and now we can add next to that, and now that should greatly change where we find it. Find it at index 0. So now if we print out, system.out.println the first, so actually if we do for int I is equal to 0, I is less than 100, then let's print out the first 10 numbers in the list, I ++, system.out.println list.get I. So here I'm printing out the first 10 numbers of the list. Oh yeah, it's L. Thank you. So we found at index 0, and the first number and because it's randomly generating numbers, the smallest random number generated was 1820, right? Because these can all be these are all a bunch of just giant integers. Anything from 0 to 2 billion is fair game, or from -2 billion to +2 billion is fair game. So that's a lot of numbers to choose from. So there's no wonder that we didn't get all there. So now if we add it, so let's go ahead and do this again. If we add, say, 10,000, that should change what we see. 10,000, right? It's going to find it at index. Oh, right, still searching for 13 there. So it's looked through -1. Okay. So found it at index 4, 0, 1, 2, 3, 4. Okay, so it seems to work just fine. And it's blazingly fast. It just searched through 1 million items, right? No problems. 10 million items, honestly, that's gonna change out how this looks, I'm sure, but it's taking more time building it than it is searching for it. I could time it. You could time it if you're interested in finding that out, but it really doesn't take that long at all. And it found it at index 53 this time. Okay, so that's binary search, which is basically the quickest way to search a list. But the condition is that the list has to be sorted already. And since it's sorted, it means it has to be made up of things that can be sorted. So if you're looking through things that can't be sorted for some reason, or that can't be put into an order, then this isn't going to help you very much. In which case, you have to iterate through every item in there. Right? So now, and again, here's the comparable, and there's a slide for the comparable interface if you forgot about it. And Arrays has a binary search method in it. So, so you can binary search an array just natively in Java. So now let's do a bit of a review for your exam by going over linked lists yet again. But this time, it's going to be a bit different. We're going to go over linked lists as a recursive data structure. Okay? And I'm not going to write any new code, but I've already got code pulled up for you. Right? So let me just go over here, recursive linked list. Right? So this one's a bit of a different one. This was provided by the authors of the textbook. And again, so first off, just to make sure you guys understand, there's no different. We're going to still use the node class over here. Okay? We're going to use the, so I'm going to remove actually a lot of the comments because we don't need them. And in my opinion, a lot of them get in the way for the node class. Okay, so here we're going to go over linked list again. The only change is that we have two constructors here because they like having that second constructor. And what this constructor does is that basically it takes in another node and it automatically sets the next node as an argument. I don't like doing that because it obfuscates a lot of stuff. It obfuscates the whole .next, and it's easier to see it if all the instructions are just there in front of you. Okay. And because then if you learn it that way, then the whole .next command becomes terrifying because you haven't even seen the .next the first time. So recursive data structures. It's often best. A lot of times we find that data structures can be defined recursively. Basically, that like they're the Russian nesting doll. Essentially, the doll holds a lot of other dolls in it. So linked lists and the trees especially, are defined as recursive data structures because otherwise they're a pain in the butt to code if you don't define them recursively. And recursive methods, they make it. Actually, the code is a lot cleaner. There's a lot less stuff to have to deal with. A lot less cases. The code is a lot simpler. So, it's simpler than the way we learned. However, you have to understand recursion in order for you to understand it, right? And I'd rather go over lists. Honestly, it was easier to throw this stuff at you first than to try to throw recursion at you first. There's some disagreement, but I find it easier just to show you that there's different ways to do this thing. And also, I learned linked lists the initial this way, not the recursive way, but the iterative way. So let's go through this. The first language developed for artificial intelligence research was a recursive language called Lisp, which it's just built off of parentheses. If you've used Emacs, right? Emacs is built with its own version of Lisp, so you can modify. If you're modifying your config files in Emacs, you're messing with a variation of Lisp, which is a recursive programming language. Recursive programming languages like that, functional programming languages, are extremely powerful. Anyway, recursive definition for a linked list. The idea here is a linked list is a collection of nodes that basically each node is followed by a linked list. Oh, wait a sec. So let me draw that. Right? I saw a couple of light bulbs, but I saw a couple of opposite of light bulbs, I guess. Just looks of blank confusion. It's easier if though it's easy. Don't feel bad because it's easier to understand, and I didn't understand it until I drew it. Right? So let me draw a linked list for you. Right? Here's a node followed by another node, followed by another node, followed by another node. I always like drawing them like four of them because that's the perfect size I feel for drawing a linked list. So, right, let's look at this linked list. This linked list is defined by a head, right? And what comes after it? Well, we could look at it as a node, but this node is the head of his own linked list. Does that make sense to everybody? Right? This guy's the head of his own linked list. So,
isn't that called root?
It's head here.
Oh, it's head.
It's head here, right? We deal with roots for trees. I like head because with linked lists we have head and tail.
Okay.
So linked list collection of nodes such that each node references another linked list consisting of the nodes that follow it. So and the last node, right? Its next is it has an empty list after it, right? So null. Okay. So a linked list is empty, so a linked list is one of two possibilities. Either a linked list is empty, base case, or it has its own node and it has a linked list after it, which is the recursive case. Make sense? Mind you, we don't call those. However, we're not going to change the programming much at all. We're just going to simply deal directly with having another node after us. Okay. So we're just going to say, so we're not going to like, a linked list isn't going to store the linked list after it. It's going to store the head of the linked list, the node. Right? Make sense? All right. So, right. So looks like this, and I'll go to the code in a second. Doesn't look any different, right, initially. What's going to be different is that we are going to, rather than keeping a size variable, we're going to actually count that. We're going to do that recursively. It's going to take O of n time, but whatever for right now. It's good for learning purposes. So let's go ahead, and what we have is this is the size method over here. Okay, it's a wrapper method, just like the wrapper method I used. So the user, when they call this, they don't know it's recursive, right? They just call it size, just like anything else. So what it does is it returns the size of the list starting at head. Okay? So here's our recursive method for it. If the list is null, well, if the head is null, that means my list is empty, right? If I don't have a head, that means I've got an empty list. So the size of the list is 0. Otherwise, the size of my list is 1 plus the size of the list that's after me. 1 plus the size of the list. Does that make sense to everybody? Okay, let me go ahead and and I'll draw it just to make sure, or I'll use this. So, right, we call size head on this guy, and he'll say it's 1 plus whatever the size of this is. This guy will say well, my list is 1 plus the size of whatever this is. He'll say it's 1 plus the size of whatever's after me, and he'll return 1 plus the size of whatever after me. So we call list, and so this calls null, right? This does the whole head is equal to null, return 0. So that returns 0. So this guy returns 1 plus 0, which is 1. He'll return 1 plus 1 to him, so 1 plus 2 is 3. And he'll return 3 over here to 1 plus 3, which returns 4 to the overall list. So this will take O of n time. It's not the most efficient way to keep track of the size. I mean, I suppose if you really wanted to save up on space and not keep track of the size, use a single integer to keep track of the size, I suppose that's a viable solution. But actually, it's more of a teaching method over here, as you understand. It's a way to get us, just to show you that we can define this recursively, right? And the code's actually fairly short, right? With a for loop, this would be an annoying thing because we'd have to do the whole current.next thing, right? So here we can just interpret this as return 1 plus the size of head.next, the list that comes after me. ToString method. Let's go ahead and look to the ToString method over here. So same thing with the ToString. It returns, let's turn this list into a string, right? So it wraps this in a private method. So node, private string, ToString, head. So if the list is empty, we want to return the empty string. And bad practice over here that they're not using their curly braces. They really should, because if they decided to add a line afterwards, then that was, it would get messy. So I always like curly braces just to be specific. If you really want to make it like short and consistent, you can just do this, right? If you really want to make it short, you can save up like that. You can do it like that, but I mean, it's always better to make it easier to read. Okay, so if head is equal to null, if our list is empty, we return a string. Otherwise, we're going to return whatever's in the list, plus, let's say they did a new line. I think I want to do an arrow, right? So head.data plus an arrow, and then that will show, and then we're going to call ToString on the next list. So I'm going to turn my data into a string, and then I'll pass the buck to the next linked list and say, okay, I'll just concatenate with whatever you've got, right? That makes sense to everybody? And the next guy goes, okay, I'll turn my data, and I'm going to concatenate with whatever's after me, and then I'll return that to you once I've got my answer, right? So again, this is easy. There's no loop to write here, and once we just get to the end, right, he'll call this on null, and we'll check it. Oh, null. We've returned the empty string, so I return the last item, which returns that to the second to last item. So we kind of build this string backwards. Okay. All right. So what about replacing something. So, so the objective of this is it replaces all occurrences of the old object with the new object. So here we're going, so this is like a mass, this isn't just set something at an index, this is change all the indices that have one thing, that have one item with it. So say I want to search the list for all the foods and turn them into bars, right? That makes sense? Or change all the A's to B's. So again, I want to take all the old objects and replace them with the new objects. Okay, so I say I want to do this on the list. So first off, our first call here, if the head is not equal to null, in other words, so long as we've got a list to do this on, right? If the head is null, yay. If my list is null, yay, I'm done. Okay. Otherwise, let me just check. Does my head have the old object? If it does, replace it. Okay. Let me go ahead and again add the curly braces I really feel like we need over here. So if I have that old data, I'm replacing it with the new data. And then I've got to, keep doing this. So I just simply say, and recursively call this on the linked list that follows me, right? Tell the linked list that follows me to replace all the old objects, all the foods with bars. That make sense? I'm telling the list that comes after me to replace all the foods with bars. I did mine, linked list, so you guys got to do yours, right? And then the next item does the same thing. If I need to change something, I change something, and then I tell the linked list after me, I did mine, you all do your thing. Right? So what about the actual important methods that we care about? Add and remove. Okay. So let's take a look at add. So our wrapper method for add and our non-wrapper for add. So here we kind of have a base case up here, which is that right? What do we need to do? So here's our first case, which is we don't have an index out, right? We're not adding to an index. We're just adding to the end of the list right over here. Okay. So the first thing is that making sure, actually, do I have a list to add to? If I've got an empty list, well, congrats. That data just became the new node and I'm done, right? No recursion necessary, right? Otherwise, I'm going to say add this data to this list starting at head. Okay. So let's go ahead and do our wrapper element. Okay. So we're just adding this to the end of the list. And I'm at the end of the list if the thing that comes after me is empty. If I don't have a list after me, then this node is going to come after me. It's going to become this head of its own list that comes after me. That makes sense? So if what's after me is empty, add it to what's after me. Otherwise, I'm going to tell the list that follows me to add this to the end of it. So if I've got an empty space, I'll gladly take it. But if I don't have an empty space, I'll tell the list that comes after me, hey, you got to add this to the end of your list. And they'll say, hey, you got to add this to the end of the list. Hey, you got to add this to the end of your list. And then the last node goes, hey, you got to, oh, wait, I'm the end of the list, so I'm going to add it to the end. Make sense? All right. So how would we do this with an indice? Well, we'd probably have to use tail recursion and keep a count of how many we did. And the other thing we'd want to do is what we'll see in the remove, which is we need to keep a track of the node that came before me. Okay. So let's start this. So say we want to remove a specific piece of data. So rather than like removing something at an index, we're saying, here's a data, I want to remove the first occurrence of it. Okay. Well, the head is null. Can't do anything about that, right? So I'm trying to remove from an empty list, so I'm not going to do that. Otherwise, if the head head data is equal, if my head has the data I'm trying to remove, I remove it. Okay? Head is equal to head.next. Right, I remove that. Otherwise, return true. Otherwise, I'm going to tell it to tell the next list, hey, here's a pointer to me just in case you need to keep track of me, right? Remove this data. Okay? So telling my old node the current head of the list. So I'm telling the head of the list after me taken me, which is as the predecessor, and removed this data. So, okay, from this guy's perspective, I'm just in the middle of the linked list, right? But from my perspective, I'm the head of my own linked list, right? So, oh, and notice that this head is a local variable. So, right, this head over here is a local variable. This head over here is the instance variable, okay? We're just giving it the same name so that we can, like, keep this recursive thought process going, okay? So I'm just in the middle of the list, minding my own business, but I'm the head of my own linked list. If I'm empty, then obviously I can't remove it, so, okay? Else if else if it turns out that I am the problem, I've got the data that I want to remove, right? Well, we've got to remove me. But I can't just remove myself, right? I have to have the guy who is before me, right? So what I do is I attach the list after me to the end of the list before me. I say predecessor.next, the node before me. Well, you attach yourself to the list that comes after me, right? And return true. That makes sense? So base case, so again, two base cases over here. I'm empty. If I'm not empty, but I have the item I'm looking for, then I say the node that comes after me, the list that comes after me, that gets attached to what comes before me. And otherwise, what I'll do is I'll tell the list after me, hey, I need you to remove this data. Here's a pointer to me in case you need it, in case you need to remove yourself. Make sense? So, and we stop once we've removed the first item. It's not like the replace method, where basically we keep going. We stop here if we just need to remove something. So this makes sense to everybody, this recursive technique? So this is a completely different way of thinking about a linked list. It might make your head spin a bit. That's okay. So that's okay. But basically, remember. But let's just review. How do we write a recursive method? We have a base case. Okay. We have a recursive case. Okay. And then we have basically the recursive cases always have to make progress towards the base case. So let's go and actually have some fun looking at some problems. So this one I'm not going to code up in Java because I think I might leave that as a homework for you guys. But we'll see. The other thing that, and really it just sees, I've got to decide what problems I want to do in class and what problems I don't want to do in class. But I think I might, yeah, I'll still do the Sudoku problem in class, I think maybe, and maybe leave it for extra credit. I'll figure that out. But right now we're going to look at Towers of Hanoi. Simplified? No, it's the same thing. All right, so Towers of Hanoi. It's a great puzzle game. Okay, it's a puzzle. Okay, the idea here is that you've got 3 pegs. Okay, left, middle, right pegs. So Towers of Hanoi works like this. The idea here is that we want to take this, these guys over here, right? These disks, and move them all from the left to the right. And you're thinking that's not much of a puzzle. I'm just gonna, grab all of them and drop them on the right peg. But there are rules, okay? So yes, there's rules to make this non-trivial. Okay, the first thing is you can only move one disk at a time. Okay, and you're like, okay, so that's no problem. I'll just flip them all over onto the middle. I'll treat it like a stack. I'll pop all the ones from the left onto the middle, right? So now it's upside down, and pop all the ones from the middle onto the right, right? Ta-da! It's not much of a puzzle. But actually, we have one more rule, okay, which is that we can't put larger disks on top of a smaller disk. And at this point, you're like, oh, now you're kidding me, right? So now it's actually a legit puzzle. We can only move one disk at a time, okay, and we can only move them from one pile. Sorry, we can't move a large disk on top of a small. If you're drawing it out, instead of using disks, I find it easier to make a stack of numbers like so, right? And especially if you're doing this on a whiteboard, 1, 2, 3, and you can't put a bigger number on top of a smaller number, right? The idea here is that I could do something like move, let's say, 1 over here, right? And then I can move 2 over here, right? And then I can move things as I need to be, as need be. Okay. So the key here of Towers of Hanoi is that actually at 3 it's kind of trivial to solve, right? You might even see the solution right now where I just move 1 over here, and move 3 over here, and move 1 over here to move this out of the way, and then I can put 2 and then 1, and then you're like, yes, okay, awesome, solved. And then I say, okay, now solve it for 20 disks, actually, or solve it for n disks, because this is a problem where we can use an algorithm to solve it, actually. Okay. Okay. So let me just okay. Obviously, if we have to solve it this way, we've got to think about it, right? So I started with 1, 2, 3, right? So let's just think. Well, I'm going to tug you along on the train of thought, right? I'm just going to, right? Your train of thought is about to get a, rocket engine, put on the back of it just so that we can push it forward. So let's go ahead and think about this, and then we'll see how recursion can help us. So what we need to do is that we need to, let's see, what did I do? I put 1 over here, right, and then 2 over here, right? And then I said, let's do this, right? I mean, doing this really didn't work because if I did it like this, 1 and 2, this really wouldn't work because then the 3 doesn't end up in the right space, right? So the idea here is that maybe what I need to do is I've got to get this, if I want to get all the other disks on top, I've got to get the bottom disk over, right? Once I get the bottom disk over, it doesn't matter what I put on top of it, right? Because then I can work on getting the next bottommost disk over. Once I get the bottommost disk from here to here, right, it's just set. It's never going to have to move again, right? That makes sense to everybody? Once I can get the bottommost disk over to the rightmost peg, it's done, okay? So let's break this down into a two-part process. Sorry, into a process. Move all the disks so let's move all the disks. So we've got n disks. Let's move n minus 1 disks out of the way, right? And then we'll move the bottom disk over onto our destination peg, okay? And then we'll take the pegs we moved and we'll try to move them back on top, right? So let's just show how that breaks up into steps over here. We move the 1 over here to get this out of the way, the 2 over here to get this out of the way, and then the 1 over here, and then move the 3 over here, and then 1, and then 2. Okay, so how did I know to do that? That's the question. Let's bring it up to 4. Okay, so 1, 2, 3, 4. Oh, okay, this becomes a bit trickier. Okay, so I need to move, okay, I need to get the 4 over here, right? So let's just ignore the 4 for a second, because we can always ignore the bottommost disk and reduce it to a simpler problem, right? Oh, that's recursion right there, right? I need to get, so if I reduce this over here, what I would really like this to end up being is that I could get the 4 over to here, okay? To do that, I need to move these three guys out of the way, okay? Which means they need to be, in order to move 4 from here and pick it up here and put it here, I need to get these 3 guys over here, right? And then I can just simply pop that up. Okay. Okay, so that reduced to that problem. Okay, once I solve that problem, whatever. Okay, so now let's think about this in a different way. Okay, so I need to get 1, 2, and 3 over here, right? Which means in order to do that, I need to get the 3 over here and get the 1 and 2 over here. Oh, do you see where I'm going with this? Move the 3, so okay. So what I need to do is I have to get the 3 over to here and put the 1 and 2 over to here. Okay? Okay, so now how do I get the 1 and 2 over to here? Okay, well what I have to do is I have to move the 1 out of the way over here so I can get the 2 over here. Right? Okay, so I can put 1 here, 2 here, then put 1 on top of 2, then put 3 over here, then put 1 over here back on top of 4, put 2 over here, put 1 over here, put 4 over here, right? So now I need to just move this guy, I got to take the 3 and move it on top of here, right? So I need to move 1 and 2 over to here, which means I have to move the 1 here. Put the 2 here, right? Put the 1 on top of here so I can get that out of the way so I can put the 3 on, so I can put the 1 over here, so I can put the 2 over here, so I can put the 1 over here. Okay, so it's an algorithm. It's only impressive because I've done this a lot of times, and I've learned how to speak really fast. So, okay. Also, I'm sorry that the eraser is dry. So actually the algorithm, I've done this as like a homework for, you know, a million times, but let's actually just see this made pretty using some graphics that, again, the book did for us. So recursion.towers of Hanoi. So let's go ahead and run this. This is a bit more involved than what I did, but it just makes it nice. So what it needs to do is that, right, the way it's going to work is that it's going to move all 19 of these disks over to here, so it can get the disk 20 over to here. Well, in order to do that, it's got to move all 18 over here, so it can get 19 here, which means 17 over here, and so on and so forth. So just using a recursive algorithm to do this.
Whoa.
Yeah, it moves a bit quickly. Sorry. So let's go ahead and play slowly, maybe. Yeah, it takes a while if we do this, but basically move the 3 over here. Now the 4's got to go over there. And it's just the same recursive algorithm. So let's see if we can't kind of write this algorithm, you know. Right. So let's go ahead and now I've done this before, but I don't have enough time to do a joke about Python. So I'll just simply but let's go ahead and look. Towers of Hanoi. It's not also just called Towers of Hanoi. It really depends on the country you're in. Also called Towers of Brahma or Lucas's Tower. Here's a really big one in Mexico City at Universum Museum, right? So that's a pretty large one. Looks even more intimidating when you zoom in. And here's you know, basically a nice interactive exhibit for algorithms. It's fantastic. It's a recursive algorithm for solving it. Now, there are ways to actually solve this without using recursion, but where basically you can use an iterative problem where you basically just rotate everything. Right? For an even number of disks, make the legal move from A to B, make the legal move from A to C, make the legal move from B to C, repeat until complete. Believe it or not, that works. Okay. But I like this flowchart, which I'll open up some other time. But, you know, the idea here is that let's go ahead and take this. And this is some, like, you know, so, new, do I have Guinea on here? I do not have Guinea on here. I love that program. So let's go ahead and just do a new text document. Yeah, I know it's not gonna stop this so that I can do a. Let's see. There we go. Okay, so paste this in. All right, so let's look at this algorithm. Let's go ahead and just move this. So, and format font. Right, the way this works in an algorithmic format is that if I want to move n disks from the source peg to the target peg using this as a spare peg. Okay? So base case, if there are no pegs to move, I'm done, right? Don't run this code. Otherwise, I'm going to go ahead and I'll remove the comments. Right? So we're going to move n-1 peg. So to move n disks from the source to the target, I take the top n-1 disks and move them out of the way, right? Then, since these things are stacks, I pop off the source stack onto the target stack. Okay? Then I print it all. I'll print it all out, sure. And then I move from then after that, I take all the stuff, all the n-1 disks I moved out of the way, which I stored in auxiliary, move them to the top of target and use the source as kind of the spare, as my leftover target. And this doesn't look like it should work, but as soon as I add the def over here, it becomes a valid Python program, which I'll just simply rename to, let's go ahead and rename it towers.py. And now, let's see, do I have anything that open? Oh, come on. Towers.py. Yes, I want to change the file extension. I'm a bloody programmer. So, edit with idle. Sure, we'll do idle. Okay. Oh, look. Okay, so run it in the Python shell. Let's see. Oh, sorry. Run. I haven't used idle. Run module. Boom. So it's a valid working program. Oh, I could give it more disks. I could make it. Let's see. I could do. Let's see. A is a list from range 1 to 20. And then I need to make a reverse copy of that, which I think is right. So now, yeah, okay, save it. So there's a, oh, right, and then I told it to move only the top 3, so 20. In case you're wondering, my preferred programming language is, in fact, Python. Now, the interesting thing about this algorithm is that it does take, and actually this is any optimal game of Towers of Hanoi, is that it takes 2 to the nth power, 2 to the n minus 1 moves. So as you can see, I don't know if you can see this, but there's still plenty of disks that need to be moved. And it's taking a while because guess what? Printing takes like forever to do.
Is it also because Python is interpreted and has to go line by line, or does Java have the same problem?
I mean, kinda. Python's a bit slower, but it's 2 to the nth power. I mean, part of it is also, if you notice with the Python program we were using, with the Java program we were using, it ran pretty quickly. So one of your homeworks will be implementing this in Java without the graphics, by the way. It's a good practice for stacks and queues. The other problem we'll be dealing with for homework is something called the 8 queens problem. And there's a lot of problems that are tough. Now, the 8 queens problem I like because it's something called recursive backtracking. So the first thing we actually have to do is learn about recursive backtracking and how to solve that. So we will resume. Right? Yeah, I want to kill it. Okay. We'll resume here back on. Let's see, Wednesday, I guess. That's the day. Yeah, Wednesday we'll resume. I'll do it if I have to. I'll do a review over the problems in class, but we'll see if I can't do a review video for you before then.